So the next question at problem 2 is looking again at the reaction that the alkene system has shown with bromine. So this is again a reaction of an electrophilic addition type. So we need to look at this and again examine the reaction of the alkene by looking again at maybe the orbital arrangement of an alkene bond. So I'm going to redraw the alkene by showing the sp2 nature across this bond as being trans. So if a p orbital overlap is shown to be a double bond, so we'll put this now in this point as the double bond. Here's my geometry of the alkene. The reaction with bromine is as follows. So the bromine temporarily introduces its own dipole, delta positive to delta negative. Maybe two bromine molecules pass in the night and induce their own dipole as shown. So this temporary dipole then means that the alkene bond breaks. The alkene is the nucleophile, the p orbital density is nucleophilic towards this delta positive bromine, and we form immediately a carbocation. So let's try and keep the geometry and shape of the molecule. So we'll draw it out and sketch it like this. So we need to consider, do we have the rehybridized bromine carbon here supporting the bromine, or the rehybridized carbon supporting the bromine here? So at this point we've got potentially two carbocations to form both secondary carbocations. So we can say, we'll just say at this point let's put the bromine in position here, and let's say this is supporting our carbocation centre. So here's our positive carbon. Then we form the bromonium ion. So the orbital here, the electron pair, can donate themselves back towards this carbon, and you form this interesting intermediate at this point, the bromonium ion. So this is the bromonium ion, and the carbocation centre, or the positive charge, is supported by the bromine. You then have the potential of the bromide to attack the carbons from either side. So let's look at the naming right of this molecule. This is carbon 1, 2, 3, carbon 1, 2, 3, 4. So it'll be named from this point. The double bond is at carbon 1, 2, 3, so the carbon bond is at 3 and 4. So let's say this is carbon 3, carbon 4. The bromide is nucleophilic and attack from two centres here, two carbon centres, carbon 3 or carbon 4. So let's just say this bromide attacks at carbon 3. The lone pair of electrons goes towards carbon 3, and we then open up this carbon to bromine bond, and we follow in this manner. So let's say attack via carbon 3. What's our product? Well, we keep in line the geometry of the molecule as we've drawn it out previously, but the bromine is at this position. It's attacking from the bottom side of the carbon, and then we open up this bond and put the bromine here. So we need to ask ourselves, why does the bromide attack from the bottom? When you consider any reaction taking place of a nucleophile attacking a carbon, then it's actually attacking the back antibonding orbital. So I'm going to put it in green pen here and then shade this lobe out, because the carbon must attack the back antibonding orbital, which is here. Oh, sorry, not the carbon, the bromide must attack the back antibonding orbital. So when we have a nucleophile approaching the carbon, we're approaching the antibonding orbital at this point, and we form this as a geometry of molecules. So if we then said attack via carbon 4, what do we then have? Well, the bromide again can attack at this point carbon 4 by the back antibonding orbital, so we'll put the antibonding orbital in over here, so it can attack at carbon 4. What do we then have? Well, we'll draw the product out as the bromide going into this orbital lobe here. So we'll put the bromine in this position, and then we'll move the geometry of this wedge into the upside, or the top part of this carbon. So we have two products that could form. Each are equally likely because the bromine or the bromide can attack from carbon 3 or 4 in equal manner. There might be an argument to say that this is the most favourable route because there's less hindrance towards this CH2 than there is for this isopropyl unit here. So if you did have attack at carbon 4, this could be more of the major isomer than this being the minor isomer too. But probably wouldn't like to guess too much as a percentage of these two isomers, but there probably would be a difference, major isomer, minor isomer, but equally you would fish some of this out of the reaction mixture. So if we looked at problem 2 in the second molecule of the reaction of this alkene system with the bromine, again, so let's just try and draw this alkene out as a cyclohexene unit, but it's not a cyclohexene, it's a cycloheptane or heptene unit. So we'll put all of our atoms in at this point. So we'll put p orbital character as the double bond as shown, and this reacts with bromine again, which is an induced dipole, delta positive, delta negative. So we attack the electron, remove the electrons out of the p orbital character towards the delta positive bromine, break this bromine to bromine bond, and again let's draw in all the carbons if we can of the heptagon that we have formed. Of the bromine and then the hydrogen at this point, so we then carry the positive charge in this carbocation centre here. So this is the positive carbocation, and then the bromonium ion forms at this point. We then have the bromide as a nucleophile likely to attack from carbon 1, carbon 2. So if we say, let's say the bromide attacks from carbon 2, it attacks at the antibonding orbital, which is this sigma star orbital we have here. The bromide attacks at the back antibonding orbital and then opens up at this point, the bromo cation. So what do we have? Being formed. So we'll say attack via carbon 2, probably not the best heptagon ever drawn. We have this system being delivered, and we say attack via carbon 1, of this molecule. And indeed, these two molecules have rotation around themselves, so they are isomer forms too. And we will consider as well in other tutorials about these reactions whether we have stereoisomers or meso or diastereoisomers, but they certainly are isomer forms of each other at this point.